Distributions or generalized functions are objects that generalize the classical notion of functions in mathematical analysis. Distributions make it possible to differentiate functions whose derivatives do not exist in the classical sense. In particular, any locally integrable function has a distributional derivative. Distributions are widely used in the theory of partial differential equations, where it may be easier to establish the existence of distributional solutions than classical derivative solutions, or they might just not exist. Distributions are also important in physics and engineering, where many problems naturally lead to differential equations, whose solutions or initial conditions are distributions. The basic idea in distribution theory is to reinterpret functions as linear functions acting on a space of test functions. Standard functions act by integration against a test function, but many other linear functionals do not arise in this way, and these are the generalized functions. There are different possible choices for the space of test functions, leading to different spaces of distribution. The basic space of test function consists of smooth functions with compact support, leading to standard distributions. Use of the space of smooth, rapidly decreasing test functions gives instead the tempered distributions, which are important because they have a well-defined distributional Fourier transform. Every tempered distribution is a distribution in the normal sense, but the converse is not true. In general, the larger the space of test functions, the more restrictive is the notion of distribution. On the other hand, the use of spaces of analytic test functions leads to Sato's theory of hyperfunctions. This theory has a different character from the previous ones because there are no analytic functions with non-empty compact support. Here's the basic idea behind distributions. Distributions are a class of linear functions that map a set of test functions, which are conventional and well-behaved functions, into the set of real numbers. In the simplest case, the set of test functions considered is D of R, which is the set of functions phi mapped from R to R, having two properties. Number one, phi is smooth, that is, it is infinitely differentiable. Number two, phi has compact support, that is, it is identically zero outside some bounded interval. A distribution T is a linear mapping T. Instead of writing it in this manner, it is conventional to write it like this. For the value of T acting on a test function phi, we write T, phi. A simple example of a distribution is the direct delta, defined by delta. Delta, phi is equal to phi of 0. Meaning that delta evaluates as a test function at 0. Its physical interpretation is as the density of a point source. Here's how a typical test function looks like. Now we shall explore the four-colored theorem. Have you ever colored in a pattern and wondered how many colors you need to use? Something like this in your painting classes or your school color book. In mathematics, the four-color theorem or the four-color math theorem states that given any separation of a plane into contiguous regions, producing a figure called a map, no more than 4 colors are required to color the regions of this map so that no two adjacent regions have the same color. Adjacent regions mean that they have a common boundary that is not a corner. A corner is a point shaded by 3 or more regions. The four-color theorem was first stated in 1852 but could not be satisfactorily proved until 1976. The 5-color theorem, which has a short elementary proof, states that 5 colors suffice to color a map and was easily proved in 1890. However, proving that 4 colors suffice turned out to be significantly harder. For over 120 years, some of the best mathematicians of their times beat their heads over proving this simple theorem, but they could not. Then, in the 1960s and 70s, German mathematician IIIT-H developed methods of using computers to search for a proof. While other teams of mathematicians were racing to complete proofs, Kenneth Appel and Wolfgang Haken at the University of Illinois announced on June 21, 1976 that they had proved the theorem. Here's how they proved it. If the 4-color conjecture were false, there would be at least one map with the smallest possible number of regions that requires 5 colors. The proof showed that such a minimal counterexample cannot exist through the use of two technical concepts, an unavoidable set and a reducible configuration. An unavoidable set is a set of configurations such that every map that satisfies some necessary conditions for being a minimal non-4 colorable triangulation must have at least one configuration from this set. A reducible configuration is an arrangement of countries that cannot occur at a minimal counterexample. If a map contains a reducible configuration, then the map can be reduced to a smaller map. This smaller map has the condition that if it can be colored with 4 colors, then the original map can also. This implies that if the original map cannot be colored with 4 colors, the smaller map cannot either, and so the original map is not minimal. Using mathematical rules and procedures based on properties of reducible configurations, Apple and Hagen found an unavoidable set of reducible configurations, thus proving that a minimal counterexample to the 4-color conjecture could not exist. The 4-color theorem was formed drawing motivation from coloring political maps of countries. However, it turns out that the theorem is not of particular interest to map makers and cartographers. According to an article by the math historian Kenneth May, maps utilizing only 4 colors are rare, and those that do usually require only 3. Books on cartography and the history of map making do not mention the 4-color property. So much for all the effort.